All right, now I know, oh, it's Ripley again. Welcome back. I know that a lot of you are probably asking, okay, how do I build this line? So this appears to have, I mean, if I had to guess, I would guess that R for this guy was around 0.93. Okay, I'm just guessing. But so when I build my line, ooh, excuse me, sorry, negative 0.93, right? Because its slope is negative. So if I had to guess, I'd probably have a line that went through about there. Now, let's have a quick little discussion about, that's supposed to be a line. Ugh. Sorry. Let's have a quick little discussion about this line right here. It's referred to as the least squares regression line. And the reason it's called a least squares regression line is what it does is it minimizes the vertical distance between all of the points, between all xy's and the line. So think about it this way. If I do this really simply, let's put it over here. If I do this really simply, and I just have like, you know, just have some points like right here. All right. Now you may say, okay, what I want to do is if I draw this line right here, because that seems to be the way that the data is trending. The problem is, I should do that, well, it doesn't really matter. Think about it. I'm going to have this big old fat vertical distance here and this big old fat vertical distance here that's going to throw off minimizing that value. I'm going to have these little guys, right? However, the problem is, and we'll talk about this with something called residuals in class, the problem is that these guys are going to make that distance too big. So what we do is we find the value that minimizes everything. So it's kind of like taking the average of the vertical distance. Really, now that's oversimplifying the problem a great deal, but we'll get to that in just a sec. Now again, just like before, you're doing all of this with your calculators in class. You're not going to have to come up with the formula all by yourself. That's a ginormous pain in the butt. But I do want to talk about what it looks like, okay? Now, there's something called the sample. Think about this as the sample LSRL, and I'm throwing in this word. You won't see this in any text, but this is going to be real consistent with what we've talked about in the past. And the way that this guy is written is it's written as y hat. And what this line is, this is the line that is created by this data. Now, remember, this right here is a sample, and it's got some n size to it. So it's not possible. Think of our SAT problem, right? The verbal versus mathematics. I go out and I grab a sample, and of course, that's going to be one of our assumptions, which we'll talk about here in just a second. Of course, our assumptions for coming up with this line is going to be one, it's got to be a simple random sample, right? All right, that's one of the biggest assumptions. All right, now, but we only took a sample. So this guy is the sample line that we created based on the information that we had. All right, now there's a population line that we don't know anything about because I couldn't go out and sample the entire population. And that's written as y equals, whoa, my thing just went crazy, beta naught plus beta 1x. Now, you're probably already going, wait a sec, Ripley, if these are lines, why don't they just write them as y equals mx plus b? All these b naughts and b ones are confusing. Well, it's going to be made worse by your calculator because your calculator actually typically writes this as y equals a plus bx. But don't panic. We know that this guy right here is going to be the slope and that this guy right here is going to be the y-intercept. Okay, it works standard issue. You're just going to have to be able to tell your calculator what you're looking for. Okay, now let's talk about the assumptions. Let's talk about the requirements. Okay, the first one, of course, is that we take it from a simple random sample. That the paired data, right? So it's all coming. We're grabbing a pair of data from a single person. So we go out, we go to a single person, excuse me, or a single data value, and I grab two pieces of information that's paired as XYs, right? Also called bivariate data. Okay, we want an approximately straight line pattern, so linear relationship, which we can test Remember back in the last relationship, we can test that. We can test using R. Remember that? Now, number 3, let's talk about outliers and see what they do, because this is worth waving our hands a little bit about. All right? Examine for outliers. Examine for outliers. Now, let me show you what can happen here. We'll deal with a couple of cases. All right. Let's say that I've got a bunch of data down here, right? And I got just this sweet linear relationship. All right? And everything's looking great. And then all of a sudden, there's this crazy value up here. Now, think about this for a sec. In absence of that value right there, we know that my line's real easy to figure out, right? It's going to look something like that. However, what does that outlier do to my line? Well, it's going to drag the line up to it, because remember, it seeks to reduce the vertical distance between the lines and the data values. So what I'll end up with is a line that looks like this. Now, you can almost think of this outlier as affecting the line the same way that an outlier affected the mean, because that's really what a least squared regression line is. It's minimizing the average vertical distance between the data and the line. So what this is doing is it's pulling this line to it. And if you notice, I mean, look, this line really doesn't describe any of the data except for maybe a couple of these lucky guys down in here. All right? So we have to look at this outlier and we have to say, okay, what are we going to do with this? Well, if we truly know that if it's an error, throw it out. Throw it out. All right? If it's not an error, so let's go 1 if it's an error. 2, if it's not an error, we got a lot of things that we can do. Try to explain it away. Explain it. In other words, try and throw it out of your sampler. Really try to throw it out of your population. Try to explain it away. In other words, away. Like with our SAT problem, let's say that we get some crazy value, right? Well, we could look at it and say, wait, this must have been either a reporting error, or maybe we were just trying to study gifted kids, and somehow a non-gifted kid made it in there. Okay? So we can either try to explain it away, or we can gather more data. Gather more data. Go chase around some more data, because that might give us the ability to fill in some data values. Okay? Gather more data is another trick. But you have to deal with outliers, because they can really throw you off. Let me give you another example of how outliers can really screw you up. Again, all we're doing is we're getting some theory down here. Let's keep this really simple. Watch this. Let's say that I have these 4 points, and they're just sitting here. Okay? Clearly, there is no linear relationship. For these guys right here, R would be equal to 0. But watch what happens if all of a sudden I throw that value out there. Now, it's clearly an outlier. It's way the heck away, or we would think at least that it was an outlier. All right? Well, what happened? I went from a no linear relationship to a very strong linear relationship. All right? To a very strong linear relationship and a least squared regression line that goes through this beautifully. These types of outliers are called influential points. Influential points. And they can really screw you up. They can make relationships look stronger than they truly are. Because remember, before that guy was here, R equaled 0. Now I'll bet you that my R is going to be, I don't know, somewhere around 0.8, maybe even stronger than that, 0.9. Okay, I can't do the R's in my head for whatever reason. All right? Now, in class, what we're going to do is we're going to go through all of the how to create the least squared regression line and how to use the least squared regression line. We're not going to do that in here. We're getting towards the end of the semester, and I don't want to drive you guys too crazy. Plus, this stuff's really not all that hard. It goes really fast, and we'll put it together with 10.2 as well. But I do want to take a little bit of time. Remember, we've got y hat equals b naught plus b1 x, right? Excuse me. And this guy right here is our slope, and this guy right here is our y int. This is a hat. I don't know what the heck that looks like. Okay? Now think about what this is really going to give us. This line is going to give us something that we can predict with. We can predict with the least squared regression line. Now we have to do that with caution. There's a caveat involved, and like I said, we'll talk a lot about that in class. However, I do want to show you this because this is a university level course. I want to show you what this B0 and this B1 truly is. And I also want to tell you a little something about the means of x's and y's, okay? All right, B1, which is our slope, excuse me, is equal to the correlation coefficient times the standard deviation of the y values divided by the standard deviation of the x values, okay? And then B0 is actually equal to y bar minus B1 x bar. Now, if you think about what this means, what this implies is that the LSRL, the least squared regression line, always goes through x bar, y bar. In fact, you can think of x bar, y bar as being sort of the anchor point for the least squared regression line. It always passes through that point because of this relationship right here. There's actually a proof of that. I think you can try and figure that one out on your own. Okay. Now in class, again, we're going to have our calculators spit out this least squared regression line. We're going to play with it. We're going to predict with it. We're going to do all sorts of fun stuff with it. But this whole idea is called regression. All right, regression analysis. And in this case, analysis, in this case we're talking about linear. Now there's all kinds of regression analysis. You'll actually see it on your calculator when we go through and we do some regression stuff. There's going to be, there's quadratic analysis, there's sinusoidal analysis, there's all kinds of stuff. And being able to do regression analysis is actually very helpful for your other mathematics classes because you'll use them to model equations based on data, which is really helpful. All right, believe it or not, you guys, that's it. That's all that you have for the chapter as far as just background material. And like I said, we'll throw these things in our calculators and we'll have a good old time with them. Thanks for your attention and your time. See you tomorrow.